Today we have a very exciting day ahead of us because Katalin has promised us to show how Pennylane works and how, at least the basics of how to do quantum computing with emphasis on quantum machine learning on this. And we will do this on the LUMI supercomputer platform, but all of the things we learned today is, of course, generally applicable also for running Pennylane, for example, on your own laptop or wherever. But as the simulations grow in size, then having access to powerful GPUs can be quite useful also. This is all I want to say. Welcome from my part, and we will kick off now by I don't know, Katalina, if you want to say some welcoming words, but after that we'll just show how to log into the system and then properly get going. Thanks.
Yeah, so just welcome, and remember that today it's all about you, so please ask questions. That's the main thing today, that you leave with a lot of learning. So let's get started.
Yes, and then I think it's Modupe will show us how to log on to the system. Please.
To log onto the system or to have access to Pennylane with LUMI, you have to have joined this project. And I believe that a lot of us have joined. And so for the purpose of this, I'll be giving a live demo on the steps to access Pennylane with LUMI. And for the purpose of this demo, I'll be showing you just a little introduction to how you can log in. And I believe, so this is the Pennylane, the LUMI web interface. And when you get to LUMI web interface, you can just click on login. When you click on login, you have 3 different authentication providers. And I believe for the purpose of this training, you would have gotten an invitation by my access ID, where you can select your institution. And yeah, just log in by your institution. Okay, however, I've logged in already on a different browser, so I'll just be using that browser to show you how you can access the environment. So when you log in, this is the screen that shows you the dashboard, and you can just click on Jupyter for Courses. Once you're on the Jupyter for Courses page, you select this project, which is the one you're invited to, and then select the course module, which is Pennylane. For the working directory, you can either choose to use your user working directory, which is visible to only you, or you can choose to use the Scratch directory, which is visible to everyone in the project. So I'll be using the Scratch directory, and then you can just click on launch. As simple as that. So yes, now we're currently on the queue, and it takes just a few seconds to have access to the Jupyter Notebook. Here on this page, you can see your previous sessions, and you can look at the output log or the job status. So now we're connected to Jupyter Notebook, and you can just click here to take us to the Jupyter lab. Okay, so this takes us to the Jupyter lab, and from there we can just click on it to start running simulations or running trying out quantum circuits. So yes, that's it for the introduction to using LUMI to access Pennylane. And you can cancel your job anytime using this button also. And yeah, that's it. Thank you. Happy learning.
Yes, thanks, Modupe.
Thank you for the introduction.
Yeah, let's just get on with the show. Katalina, the floor is yours.
Perfect. All right. Perfect. So today we're going to talk about quantum computing. We're going to do a small emphasis on quantum machine learning. Before, let me introduce myself. I am an engineer, so I don't know the background of everybody here in the room. So some people had a PhD in quantum computing. You have moderate experience, so I'm guessing you might come from various backgrounds. Just so you know, you don't need to have a PhD in quantum computing to understand what we're going to talk about today. We're going to give a small overview of what we do and what Pennylane does and what you can do, and that's the most important, what you can do with quantum computing. I've worked on various roles. I worked at IBM for a while, and then I joined Xanadu. So I'm going to mention Xanadu a little bit. I work as a quantum community manager, which means I work with people in the community like you, everybody attending today. And my goal is that you can really use this as a tool to do your project. So I wanna help you do your projects. And if you have any questions afterwards, I will point you to where you can join the community and where you can ask questions. The main thing is, why do we even need quantum computing, right? We are not going to use quantum computing for every single problem. We're only going to use it for very hard problems that are particularly suited to quantum computers. So chemistry is an example. Quantum computers work with physics that is intrinsically different to the physics of classical computers, right? What we know as classical computers. So it's not about having just a larger or faster normal computer. The physics of how it works, it is intrinsically different. So chemistry problems are particularly suited for that because they exhibit the same quantum properties that you see in quantum computers. So quantum computers, you don't have to program the math to explain or describe how something like entanglement or superposition or interference, you don't have to, do a mathematical approximation on a classical computer. You can actually create them in your quantum computer. So you don't have to, do all of this mathematical description to describe these quantum phenomena. I'm not going to focus on what they are, on how they work, but it is important to know that they are specific to like very little things. This is not something we see in our real world. And it's something that we can create in a quantum computer in different ways. There are many technologies, and they all have the common ground, or there may be some that are slightly different, but the goal is to replicate those quantum phenomena so that then you can do simulations and you can perform calculations that would be very hard. So in chemistry, if you want to understand to a very precise level how a molecule, what are their energies or how it will react with something else, you can actually create a simulation with a quantum computer that can help you analyze and understand those chemical systems or chemical processes. Optimization is thinking, we have this capacity of embedding problems into a quantum computer and extracting an answer and analyzing. So what if this was not a chemistry problem, but what if an optimization problem could be mapped into what a quantum computer can do? And can we use these quantum properties to explore other systems, not only systems that physically exhibit those quantum properties? Can we map our problems and use this new kind of computation to solve other problems? And the answer is yes. So optimization and machine learning are cases where you use classical and quantum computers together to try to solve those problems that we have in the classical world. Not every problem will be well suited, and this is a fine line that it's an active area of research still. What makes some problems useful to solve in a quantum computer, and which ones are not particularly suited for that? And the hard thing is that our quantum computers today are not very good. Our quantum computers today are small and noisy, and that's the main thing. They have a lot of noise that doesn't allow us to do very powerful computations because our information just becomes rubbish after you have too many qubits or too many gates. you cannot really extract anything from that information. So the field as a whole is working towards something called fault-tolerant quantum computing, which means creating quantum computers that have error correction in them. And this way you won't have those errors. So you won't have a quantum computer that, it's like if you had a calculator and you add 1 + 1, and sometimes it says 2, sometimes 3, sometimes 1. This is not what you want from a calculator, right? So we're building error correction into our quantum computers so that we can get to tackle those very hard problems. But this is something that takes time, and this is something that is going to happen in the future. So for now, remember that quantum and classical work well together. So you're rarely going to see a quantum computer doing everything. Actually, I don't think you can see a quantum computer doing everything. You will always see a combination of classical and quantum working together. So you don't have to worry about, you will still need supercomputing centers. You will still need clusters, and they will work together with quantum computers. And the other thing is, most of the problems today are toy problems. Today, quantum computers are not yet at the level that we can solve problems useful for specific applications. But as more people come into the field and bring their own diverse expertise and vision, then we can maybe find problems where there is an advantage, or we can also design new algorithms that don't require so many resources from quantum computers. So aside from that introduction, I will talk about Xanadu, Pennylane, quantum machine learning. We will go into a short demo, and then we will shortly talk about some other applications and tools. I saw that a lot of you had very interesting interests. So Xanadu is a fault-tolerant, it's a full stack quantum computing company. That means that we do everything from the hardware to the software to the applications. Our mission is to build quantum computers that are useful and available to people everywhere. And this mission is very important because it has two parts. On one side, it focuses our efforts on hardware. We want to build quantum computers that are very large. We would need probably thousands of qubits to be able to solve useful applications. Our qubits are our main unit of information. For those who are beginners here, they are kind of like the equivalent of the bit, but they work differently. And the second part, available to everywhere, it means it doesn't matter if we have the best technology. We want people to use it. We want you to use it and to solve applications and to research with it, because it's people using it that actually makes this a very powerful tool. So we do want to have this first part. We want to build quantum computers that are very powerful and useful, but we also want to help people use it. And this is why we do a lot of efforts on education, on Pennylane, etc. In terms of our hardware, we use photonics. So our quantum computers are based on light, laser light in particular. So we have pulses of laser light that travel through fiber optics. It's actually the same fiber optics that probably takes internet to your work or home, if you do use fiber optics. That fiber optics, you can see it in the picture on the left and right. And it carries that light in a very good way, right? So light travels very well on fiber optics. And then in the middle, you see a chip. That's a silicon nitride chip that allows us to modify that light. So if you're thinking, can I use just any laser to do quantum computing? And is that enough? You need a little bit more. So you need to modify that light to create special states that can act as qubits. So in those silicon nitride chips, you have waveguides. Those waveguides are like holes or like narrow corridors in that chip, and that modifies the way the light behaves. That light, those pulses of light, are made of many photons. So it's a many photon approach, and the way those photons have to move around in those waveguides, it modifies the state of the light, and then we can use it to perform quantum computations. So it becomes quantum light, and then we can do fun stuff with it. Now, Our full stack approach, I mentioned, goes from design of the hardware, the design of the architecture. So how are we going to build these quantum computers? Like, what is the math behind them, etc.? How are we going to build these error correction codes, etc.? So we have this architecture side. We have the design of the hardware, which does include some chips, and we have to put it together. So a chip on its own, fiber on its own, it doesn't do anything. You need to put it together into a complete system. So this is a key part of what we do too. In terms of fabrication of the chips, we have partners. We have partners that fabricate those chips. So we're very happy to work as an ecosystem for the fabrication and really to leverage the advantages of everyone. And in terms of software, of course, we need to use those quantum computers. And for that, you need a lot of different layers of software. So you have some software that is made for designing the quantum computers. You have some software for using them. And the main software is Pennylane, which is the one that you're going to use today, and the one that is going to let you do projects. In terms of applications, we have two main areas of applications research. So we have one on algorithms and battery simulation. So designing better algorithms and doing research on how to simulate the batteries of the future, how to make better batteries. And on the other hand, we have quantum machine learning. So we have some of the best experts in the field, in the world, like Maria Schuld, working on the fundamentals of quantum machine learning and how quantum machine learning works, why, how can we make it better, etc. Now, a quantum computer, even a photonic one, can have many different versions. In 2019, we created the X series generation of quantum computers. There is actually still one quantum computer called the X8 on the cloud, usually only recommended for photonics research. And this is non-universal, but it was the first photonic quantum computer ever put on the cloud, and it's still available there. Now, the next generation was Borealis. So Borealis made the headlines everywhere. It achieved quantum computational advantage. It's a huge feat. It's a programmable quantum computer that is using the time domain. So it works very differently from the X series chip. But again, it's not universal. It was designed just to solve one problem, which is Gaussian boson sampling, which is a problem that is known to be very hard for classical computers to solve. So Borealis is not a chip. I know that I put it as the same size as the X series chip. It's not a chip. Borealis took an entire optical table, so maybe 2-3 meters long by 1 meter wide. It was a very important experiment. It showed what you can do with quantum computing. In the experiment that was published in Nature, we had 216 Q modes, which are sometimes we call them squeeze state qubits. So they're like a special kind of qubit. And this device could get up to 288 Q modes. Now we've already achieved, quantum computational advantage, and the next milestone is fault tolerance. So we are in the process of building our first fault tolerant quantum computing modules. This is a huge endeavor, and the specifics of how this works is different. And this quantum computer is actually universal. So these fault tolerant modules that we're building are actually universal, and they're based on something called measurement-based quantum computing. This is a very interesting technology, so definitely worth learning about, and it's different to maybe what you have been exposed to. So for those who have like intermediate experience, you may not have heard of measurement-based quantum computing, but it has huge advantages. And what you see here in the picture are just different layers that are kind of like the components of what these modules look like. And the goal is to be able to have these quantum data centers or hybrid with classical quantum that can allow you to solve meaningful problems for the world, for industry. So in measurement-based quantum computing, you prepare your qubits, you entangle them, and then it's at the moment of measurement that you apply your gates. So you can code your circuit like you always have with Pennylane, and then on the back end, you have a compiler that is transforming that into a specific setting that will perform a measurement in a specific basis. So it will perform a specific measurement depending on the gate that you want to apply. So performing a measurement is equivalent to applying a gate. And then the result of that measurement is what you analyze, and what, again, the compiler can translate it to something that you can understand and interpret. So definitely worth reading more if you're interested in this technology. Some key advantages are, well, using photonics is very good if you want to scale, right? I mentioned you will need maybe thousands of qubits to be able to solve meaningful applications, because we use technologies that have been perfected and highly developed by the telecom industry, like fiber optics or using silicon processes, silicon nitride. Then this is something that can really scale. And you can modularize it. You don't have to put everything inside of a cryostat, which is something that happens in other technologies. So if you can, have almost everything, we do have one little part that happens inside a cryostat, but you can have almost everything at room temperature. Then you have a lot more flexibility. And because you're, again, using fiber, you have more flexibility for performing error correction codes, because you can just move the wires around, and then that can allow you to perform different error correction codes. So you don't have to, if you already printed out a superconducting chip, everything is there, and you don't have any error correction flexibility. So we're very happy to partner with different different companies in the industry on every side of the stack. So hardware, software, and applications. You're gonna see on the hardware, I think it's mainly obvious. On the software side, Pennylane interfaces with a lot of different kinds of hardware. So you're gonna see a lot of that. You can use classical and quantum hardware and software, and it's designed to interface properly with all of them. And there's also startups that have built their stacks on top of Pennylane. So, for example, there's one that does quantum finance, and they have built their finance, part on top of Pennylane. So this is great. Pennylane is the base tool that can allow you to develop your own technologies. And in terms of applications, you're going to see mostly we've worked with a lot of car manufacturers that are interested in our battery research. Now, Pennylane. Pennylane is a software. I mentioned it's a software library for programming quantum computers, but it's so much more than that. Xanadu is the main maintainer, but Pennylane is a community project where we have an excellent documentation, a community project where we have events, we have talks like these, and well, it's the place to go. So if you go to pennylane.ai, that is really the place to go to learn about the latest research, to speed your research and basically your work and your learning on quantum computing. So even though Pennylane, it's a Python library, but it's so much more than that. It's a community. It's a place to learn. So definitely, if you forget everything else, that's okay. But remember, quantum computers work as a hybrids. They don't work for everything. And Pennylane.ai. Those are the two main things you need to remember after today. We are, I think we're already at 2,000 GitHub stars, or maybe we're missing a couple of starts to get there. So definitely give us a star on GitHub if you can, and attend our main event of the year, which is called QHack. one key difference and something that makes Pennylane very special is the fact that it's made for differentiable programming of quantum computers. So if anybody here comes from machine learning or from the classical world, you know that differentiability is key in order to be able to do training. And so differentiability was built at the base, at the core of Pennylane. And so you can train quantum computers, you can have different differentiation methods. This is something that is done automatically for you. So this can help you a lot to integrate with classical machine learning workflows and to, yes, basically to optimize and to do machine learning. Now, in terms of modularity, I mentioned you can integrate quantum and classical. This happens very well because we use something called Q nodes. So if you see Q nodes, you're going to know that there's Pennylane under the hood there. They encompass everything that is quantum, and they contain it into the Q node. And so then you can have classical inputs and a classical output, and this way you can connect to other parts of your workflow that are classical or quantum as well. So we use Q nodes to contain everything that is quantum. Now, here we see an example of a circuit. You start with an initial state. Usually you start with 0, but you could start with something else. We have some templates, which are some functions that you can use for state preparation or embedding your information, for example. Oh, I see there's a question. Do you plan Xanadu educational internships, other programs in Europe, or available online? We do have an internship program. It's called a residency program. The applications close on December 8th. So if you are interested, you should apply as soon as possible. Don't wait until the last day. And it is in Toronto, but we cover the expenses. Like, we buy you the plane ticket to come and like the visa, and it's a paid internship. So you will be able to live in Toronto. It's actually so much fun and so much better to have everybody on site. So I definitely recommend to apply. It's a competitive program, right? You need to be very good, but like, please do apply. We want the best talent, so definitely apply and show the projects that you have done. So going back to the slides, we have some qubits. So here, the horizontal lines are your qubits, but we call them wires. In Pennylane, they're called wires. This kind of is inclusive of technologies that don't use qubits. So that's why we call them wires. You have, in this case, 3 wires, which are 3 qubits. You also see some parameterized and non-parameterized gates. So, your Hadamard and your CNOT are non-parameterized, but you have your X rotation, your Rx, and your Ry, which are indeed parameterized. So these parameters, you will often have something like a variational circuit where you will iterate over them in order to get a better results over time. And for the measurement, we use the measurement as the return value of your Python function. So your quantum circuit is going to be a Python function, and then the return value of that Python function is the measurement. Every Q node, for it to be a Q node, it needs to have a measurement. And even though I mentioned Xanadu has some hardware on the cloud, I generally only recommend that for photonics. So if you're interested in photonics specifically, if not, probably the easiest is if you start with using something like Amazon Bracket. You can use some other technologies, or you can interface with Qiskit, with the IBM Quantum experience. You can run your experiments on IBM computers. Of course, you have to get their own account and you have to follow their own rules. So IBM only gives you like 10 minutes of quantum computer. So make sure to use simulators first. That is like the best recommendation I can give you. Do everything you can in a simulator. And then when everything works very, very well, and if you really want to run it on hardware, then do so. But don't wait your precious minutes of hardware. In terms of simulators, Pennylane has a lot of built-in simulators. The best ones, in my opinion, are Lightning Qubit, Lightning GPU, and Lightning Cocos. So I don't have Lightning Cocos on this slide. I have it in a future slide, in another slide. So in general, if you want to use CPUs, you would use Lightning Qubit. If you want to use GPUs, NVIDIA GPUs, you would use Lightning GPU. Or if you want to use LUMI systems, for instance, you have Lightning Cocos. If you have AMD GPUs or other, everything that is supported by Cocos. Default mixed is if you want to use, if you want to have errors or noise, if you don't have noise in your systems, you would use default mixed. Now let's go and try our first example. Let me see. All right. So we're gonna first create a Jupyter notebook. So we're gonna click on notebook. So how do we convert a quantum circuit into a Q node? How do you think that works? Or why would we need a Q node? Okay, this is something we will get to answer later. All right, let's start then with importing. I'm going to do live coding, so please be ready. I'm going to start now. Let me know if the size is right. I can also zoom in a little bit. Maybe this will be better for you. We're going to start with import Pennylane as QML. And from Pennylane, import NumPy as NP. So this is a wrapped version of NumPy. Now we're going to start by creating a device. So my quantum circuit has to run somewhere. We're going to start with a simulator. So we define our device with dev equals qml.device. So qml.device, let's just choose the device. The first one we're going to use is lightning.qubit. So lightning.qubit, close, close the text here. And I'm going to choose how many wires I want. So I'm going to choose wires equals 2. So this is how many qubits I have. Now I'm going to create my Q node. So I'll do @qml.qnode. So this is kind of our signature line. And I will add the device here, dev. And now I can create my circuit by creating just a Python function. So I'm going to call it circuit, def circuit. And I have some empty parentheses because I have no arguments.
Can I ask a question? What lightning qubit means? I missed probably this.
Totally okay. Lightning qubit is the device or the simulator that we're going to use. Lightning qubit is our, it's built on C++, so it's fast, and it's for working on CPUs. So Lightning qubit is, I'm going to say, my favorite simulator, Pennylane simulator for running on CPUs.
Thank you very much.
Mm-hmm. So you could alternatively, for example, use default qubit or default mixed if you were going to run something with noise. If you're going to add noise to your circuit, etc., you would use default mixed. And later we're going to use lightning.cocos later. But for now, let's stick with lightning qubits. So great question, yes. So we're defining a circuit, which is just a Python function. We're using this decorator on top. So this add.qml.qnode it decorates the function, so it modifies it to tell my program that this is indeed something quantum and it has to run on the specific device. If I wanted to run on hardware, for example, I could use it here as well. So I could, if I had the Qiskit plugin, for example, so we have plugins. If I pip installed Pennylane Qiskit, I guess you cannot do it today, but I could use, for example, IBM computers, or if I used the Amazon Bracket plugin, Pennylane AWS Bracket plugin, then I could run on an QERA device, for example, or some other simulators as well. All right, so within our circuit, we're going to start adding our gates. In this case, we're going to use a Hadamard and a CNOT. So we're going to create entanglement. So QML.Hadamard. And we're going to tell it on which wire to act. So on wires equals 0. So this is, I'm going to place this particular gate Hadamard on the first wire, which is wire 0. Notice that even though I have 2 wires, they are 0 index. So the first wire is wire 0. The next gate that I'm going to add is a CNOT. So QML.CNOT. And this gate takes 2 wires. So wires equals square brackets 0, 1. And I close my parentheses. So 0 is the first wire that I'm passing here. It's the control qubit, and 1 is the second one, so it's the target qubit. So I'm going to have a CNOT where the control is on 0 and the target is on 1. And my return value, I will return QML.props. And I have these empty parentheses. Oh, right. So I can now print the value of my circuits, for example. And I get a 50-50 chance of getting 0, 0 and 1, 1. So the first value here is 0, 0, right? You know, because you measure the probability, you know, the only options once you measure are 0, 0, 0, 1, 1, 0, and 1, 1. So you have 50% chance of getting 0, 0 and 50% chance of getting 1, 1. Note that we use big endian. So let me draw the circuits now. So we're going to use QML.draw_MPL. We're going to pass the circuit and some empty parentheses at the end because our circuit doesn't take any arguments. Oh, I think we don't have MATLAB. Okay, we're going to use just QML.draw and we're going to print it. So we're going to print QML.draw. So if you're running locally, for example, and you have MATLAB, then you could print it nicely. But if we don't, that's okay. We can print it like as ASCII. So you see qubit 0, you have a Hadamard, then this is how you show that you have a CNOT, you know, the control and the target, and you measure the probabilities. All right. So this was our hello world. So then we can draw it nicely. We can use QML.draw_MPL. That's okay. That's okay. We can print it, you know. It's good that you see this as well. Also, very large circuits, you can never really print it with MATLAB, but you can always use this other option, which is using just the ASCII printing. Here you can probably see it. All right, so this was our hello world example. Let me know if, aside from the MATLAB thing, any other questions, any thoughts? Easy, right? So give me a thumbs up if this is easy. That's a goal. That's a goal. Now, you can do other things. So, for example, I could add another gate, a parameterized gate here, for example. So let's say on wire number 2, I'm going to add QML.RX. This is an X rotation. Oh, I see a question in the chat. Python version needs to be at least 3.9. I actually recommend 3.10 or above, or 3.10 is good. But yeah, no, not 3.6. 3.6 is not supported. QML.RX, and we're going to add an angle because it's an X rotation. You need to rotate on a certain angle. So let's say theta. And we're going to add this on wires equals 1. So on the second wire. Now, theta is a parameter. So I can add theta here as an argument to my circuit. So theta. And I can use NumPy. So theta, like the value I'm going to use later is np.array. Usually you define it as np NumPy arrays. Let's say it's going to be 0.5. All right. Now we're going to add it here when we're going to print the value of our circuits and the drawing. So I added theta as an argument to my circuit. I added this new gate, an RX gate, an X rotation, which takes an argument, theta. I created the value for theta, and then I added it at the moment of printing the circuit and the drawing. And you see that the probabilities changed, and I can see it here in the drawing of my circuit. All right. What if I didn't want to return the probabilities? We often use expectation values. That is what we use most often in quantum computing. And for the people who are doing PhDs here, you know, expectation values are important. Oh, I see there's a hand up. Anastasia?
Yeah, I'm wondering about wires. What is the difference between wires zeros and wires? It's like layers. So we apply C nodes on 2 layers, like from 0 to 1. And for example, RX gate, we apply only for second qubit. Or how does it work with wires?
Yeah. So wires are like saying qubits, right? So this is like qubits equals 2, right? Except that qubits is not the right word. We use the word wires. Remember how, let me go back here. They kind of look like wires. If you look at them, if you notice in the circuit, those horizontal lines, which represent your qubits, they kind of look like wires, right? And the thing is, in technologies like the previous ones we had, let me go back. In our X-series chips or Borealis, they technically don't use qubits. They use something called Q modes. And so in order to have a comprehensive language that would include everything, Q modes, qubits, then Pennylane decided to call these wires. So they look like wires when you draw them, or even if you go here, you know, these horizontal lines, they kind of look like wires. But what this means in practical, you know, for all practical purposes, it's like saying qubits equals 2. So in Pennylane, it's important to know that wires is kind of like our keyword for saying qubits. So wires equals 2 is we're creating a device using the Lightning qubit simulator, which works on a CPU, and we are using 2 qubits.
Thank you very much. It's clear now.
Okay, perfect. Awesome. So now we have an example with 1 parameter. Now, what if we wanted to optimize this parameter? For example, what if we wanted to create an optimization routine? How would we do this? We can do this by creating an optimizer. So let's say opt equals, we can use one of the ones that come with Pennylane. So QML.gradient descent optimizer. Oh no, before that, sorry, I missed something. My return value is empty. So what if we don't want probabilities, what if we want an expectation value? This is something that we often have. It's very, very common in quantum computing to want to use expectation values. Because something that I didn't mention is you sometimes have shots. So I could define shots equals, like, for example, shots equals 1. Let's go back to probs. Let's say theta equals 0. That way that gate isn't doing anything. So shot equals 1 means, what if I just ran the circuit once and got only one measurement? What would we get? See how this time we get a 1 here instead of the 0.5 and 0.5 that I would have expected. So this is not like, this is not, yeah, and now on one of these experiments, I get a 1 on the last one, right? This is kind of not what we want. Usually you have a lot of shots. If you don't specify the shots, it's like using infinite shots. And you often use expectation values kind of to average over, let's say, a very, very large number of shots, like an incredibly large number of shots. Okay, perfect. I see, Anastasia, you have 0.502 and 0.498 with 1,000 shots. Yes, exactly. So you can see the law of large numbers coming into play here. If I only throw my coin once, I don't get, I don't get anything close to what if I throw it 1,000 times or 8,000 times, for example. And if you don't specify the number of shots, it just gives you what should be like the theoretical answer. Now, if I don't want to use probabilities, I can use the expectation value. So I use expval, qml.expval, and I will measure an expectation value of measuring with respect to a specific observable. So in general, what we use is qml.polyz. I will measure, in this case, I will measure the first wire. So wires equals 0. So qml.polyz of wires equals 0 means I'm going to measure this specific observable. So it's like measuring on the z-axis, measuring on the computational basis. And I'm going to get the expectation value over a very, very large number of shots. So I don't define the number of shots here. And let's see what we get. The expectation value is 0, which is perfect because let's say shots equals 1. Let's say what we get -1, which means we get a measurement on the negative z-axis, like on the polyz's eigenvalues are -1 or 1. So if you're pointing to the south pole of the Bloch sphere, you're getting a -1. So if you have a 1 state, it's the negative z-axis, so you get a -1. Or if you get a 0 state, if you get a 0, you're pointing on to the positive z-axis, so you get a 1. So if I run this enough times, I will hopefully get a 1 at some point. Or not, there might be a seed somewhere there. Oh, here, I get a 1. So this means on one of these runs that I made, I got 0, so I'm pointing on the positive z-axis. And if I don't have any shots, like normally it should be 50-50, the probability here was 50-50 because my Rx is doing nothing. So my expectation value is 0. So I know this was a little bit confusing, but my expectation value is like half of the times I measure on the -1 because it's on the negative z-axis. Half of the times I get a +1 on the positive z, and then the expectation value, average value, let's say, is going to be 0. All right, now that I have an expectation value, now I can do some optimization. And this optimization is the key that goes before doing machine learning. So it's important. We create an optimizer by using opt equals QML dot gradient descent optimizer. I could use also an Adam optimizer. I could use something else. I can choose a step size. So I can say step size equals 0.2. Of course, this will depend on your problem. This is not something that will work for everything. And now I can start doing the optimization. So I will use a function called step. So for a number of iterations, so let's say I'm going to do 10 iterations. For it in range 10, I'm going to get the new value of my parameter theta. Theta equals opt dot step. I'm going to add my cost function. In this case, my cost function is just my circuit. So my circuit. And I'm going to add the first value of my parameters. In this case, it's theta. All right. Now I'm going to print the new value of my circuit. And I'm going to print, let's say, theta. And I'm going to print theta. Also gonna write here circuit so that you see. Usually this would be the cost. Usually you would have a cost function. In this case, we just have the circuit. Okay, you probably started at a bad point. Let's choose. Oh, and we also have to set requires grad. Requires underscore grad equals true. So this is why it's important to use the Pennylane's wrapped version of NumPy, because we can add this specific wording here, which says that this parameter is trainable. So requires grad equals true, it means I am going to train over this parameter, over the specific parameter. So let's start somewhere else. Let's start at like 0.5 and let's see what we get. All right, this is not normal. I may be doing something wrong. Let me define a cost function. Let me define a cost function and return the circuits. And here we write the cost. All right. All right, this is not normal, so let me just check. This is what happens when you do live coding. So give me a sec. Oh, I probably need to do something like squared or something. You're right. I'm adding the Rx on the second one. I should use wires equals 1. Or not even. Anyway, this is just an example. And of course, it's not a great one. Not a great example this time. Okay. Matplotlib is now installed, but we can use it for later. So we can use it for later. For now, just believe me, it does work. So right now, it's not working, but it usually does. It usually does. So for this particular example, I probably messed something up, but it usually does work. So let me just look at my original example, which I modified a little bit. Let me see what I did differently. Let's have the original example that I usually do. So we're going to have, in this case, let's try using a single wire. Wires equals 1. Let's try, actually, you can just have 1 rotation on wire 0. You can just have 1 rotation on wire 0. You can draw your circuit, so you have just 1 rotation. And let's see. Okay, perfect. So it does work. So believe me, it does work. It was just a poorly chosen example. Adding that entanglement wasn't great. But in this case, you see I have a circuit with an X rotation. It runs on my wire, which is just a single wire. I get my expectation value on that poly Z. I start somewhere. I could start anywhere. I can print my circuit and the value of my circuit, and I get, like, I can create a cost function if I want. I could like square this if I wanted, for example. This is like the cost function is a classical one. You notice there's no Q node here, so you could use, like, for example, the absolute value squared. Like, this is something you often do in machine learning. So you could totally do that in your cost function, and you will get an optimization here. So this is very useful. You can see the flexibility that you have. The first part, you know, it was clear, you create a quantum circuit. And the second part is you go back to your knowledge on optimization, and you can choose different optimizers, etc. And eventually you could use, for example, PyTorch or JAX if this is something that you're used to. All right, so I see some messages on the chat about using the Pennylane-G reservation for faster job submissions. So maybe you can show us later how to do that. For now, this was like the more beginning example. So now you know how to create quantum circuits. You know how to create an optimization routine. Now let's talk about machine learning. So let me go here and let's talk about machine learning. All right, so let me go back to see the chats. I see, oh, there's a Pennylane. Thank you for sharing that example. Yeah, there are a lot of examples that we have. Yeah, so in the reservation using the Pennylane-G. Okay, thank you. All right, so now we're going to talk about machine learning a little bit. It's all about finding patterns in data, and there's often some confusion with optimization and machine learning. People may disagree on this, but really data is key in machine learning. You will not have only a single parameter that you optimize. You also won't have specific instructions. You will use data and try to find patterns on it. So whether it's classification, regression, language models, whatever it is, you generally need data and finding some kind of pattern in it. And you don't hard code them. So in this case, you know, let's say we had the previous example, we had our X with some theta. Here we have alpha and beta. We're not getting a knob and like moving it around. We don't hand code it, we actually learn it. So in the previous example that we did in the code, we taught the circuit to modify the parameter theta in order to get a lower value, a lower expectation value. So basically, we're teaching that circuit to move the rotation closer so that we can get on the, like a minus, a -1 on the expectation value. Or, if you modify that cost function, then you get either closer to, closer to somewhere else, but you're modifying, the behavior of your system, not by hand coding it, but by learning it. So often you're going to see these cost functions with these like nice shapes that look like a mountain. We're going to find the parameters alpha and beta that allow us to be as slow as possible on that cost function. This is where gradients become so important. So gradients are the direction of maximum change of your function. And we're going to go often use some gradient-based methods, although that's not absolutely necessary. You could use other methods, but if you use gradient-based methods, it allows you to, go against the gradient, so you can go downhill. These are, let's say, they're not guaranteed to work in every situation. In some cases, they don't work, but they are very useful in many cases. So how do we do differentiation? I mentioned gradients and differentiation. Can you do that on hardware? So I'm going to ask you, everybody in the chat, can you do, let's make a guess. Can you do backpropagation on quantum hardware? No, I get an answer that says no. Yes, you can. Okay. More people saying yes. Actually, you cannot do backpropagation on quantum hardware. So you have to find other techniques to do differentiation. It's the backward pass fails. You cannot find those errors and propagate them there. So what you do instead is you can use other methods, such as the parameter shift rule. And so if you have like this hybrid workflow, your quantum part would be like a black box. Let's say you're using PyTorch. PyTorch is asking for a gradient. Pennylane gives it a number, but it is treated in the program kind of like a black box, and then you can continue. So this is a way that we can integrate, backpropagation happening in PyTorch, for example, and Pennylane using its own, whatever differentiation method is best for that specific hardware. And so this is something that Pennylane does under the hood. You can specify it if you want. Like if you want to try out and compare different differentiation methods, you can totally do that. And there are some that work on hardware. So let's say the least recommended one is finite differences. Finite differences can accumulate a lot of errors. It's approximate. Instead, the parameter shift rule is exact, and then you don't accumulate errors and you do get the exact value. How does this work? You can see it in the blue callout here. You run your circuit twice with a shifted version of your parameters. Unlike finite differences, this is not a small shift. This can be a big shift. And then you multiply it by a constant to get the value, the analytic value of the gradient of that function. So we have what we call gradient recipes in Pennylane that are there under the hood. You don't have to worry about them. And they allow us to calculate those gradients on actual real quantum hardware. This is slower than using backpropagation, but backpropagation doesn't work on hardware, so on quantum hardware. So this is a very good option if you're running on quantum hardware. If you are running on simulators, and this is what we do most of the time, so I do encourage you to use backpropagation or adjoint differentiation. This is another method, and it's the one that actually works with Lightning Qubit and Lightning Cocos and Lightning GPU. It's adjoint differentiation. It's already coded for you. And this one is the fastest one. This one works really fast. So my recommendation again would be make sure to acknowledge that not everything that we can do in the classical world can work in quantum, but there are some things that we can do to bridge that gap, even though it will be slower. Now, once we have that, then we can create those variational algorithms that I mentioned before. So you can start with a specific ansatz. And so this ansatz, it means like a specific layout. So some specific gates that you're going to add to your circuit. It doesn't really matter what parameters they have. They're just the layout of your circuit, the specific gates that you're going to add. You can have different kinds of ansatz. Notice how in these boxes, you have these kind of blue boxes, you have everything that is quantum, but then the measurement at the end returns something classical. So you get this expectation value. This is what we mean by this like symbol here. We have an expectation value of a specific observable, and it's going to be a function of either my data, for example, here, X, it represents non-trainable data that is important in quantum machine learning. And you have some trainable parameters like we had in the example we did before. We had theta, which was indeed trainable. And you can have many thetas. Here you see theta 1, theta 2, and you can have several data points, so x1, x2. You can combine them, so you can use either several circuits or a single circuit or combine quantum and classical to build your cost functions. And this is probably the hardest thing, probably one of the hardest things to do. It's how to build the right cost functions that will represent your problem and that will allow you to perform proper optimization, that you won't fall on the wrong side. And finally, you have a training procedure. So you can, like we did before, you can optimize those parameters to find an answer to that specific cost function. So whether you are performing a classification task and you're, if you're trying to minimize some kind of metric, this is what you will try to do in your training procedure, depending on your cost function. Quantum machine learning models can look very similar to what you would see maybe in some classical machine learning models. But in this case, so you start with an initial vector, it's your initial state. And you program all of these gates, which are matrices. So you have a lot of linear algebra. All of this is just vector matrix multiplications, except for the measurement at the end, right? Which is a nonlinear, you have nonlinearity there. And then, as I mentioned, some options are using gradient-based methods, but they're not the only ones. So you do have other methods to perform optimization and machine learning that are not gradient-based. And here you see a nice picture of how one of these hybrid computations could look. So you could have a part of a circuit or a circuit running on a superconducting qubit quantum computer. You could have some classical processing after that. You could then run part of it on a photonic quantum computer, do some more classical processing, and get an answer at the end. So they really complement and extend machine learning models. And you should use them when it's relevant and important, and explore, of course, for whatever applications you're working on. These are some examples of recent research that we've been doing in quantum machine learning. So understanding contextuality and inductive bias, graph embedding your data into your quantum computer, into your quantum circuits is a very hard, it's very hard, and it's often a bottleneck. So you will see that a lot of people are trying to, put a lot of images into a quantum computer, and the quantum computer is not particularly suited for that, right? So that's part of inputting your classical data into your quantum computer can often be a bottleneck. So you have to be either very smart about it or choose a problem that is particularly suited for a quantum computer. Other things that are important to know are specific algorithms. So if you're starting or like intermediate in this, I would totally recommend, if you're intermediate or advanced in this, I would totally recommend trying the QSVT algorithm. It's one of the most advanced ones, and it is like, it can be seen as a generalization of other algorithms, like amplitude amplification, for example. So very popular algorithm right now, we have a tutorial on this. So all of these that I have showed before, and these two as well, we have demos on the Pennylane website, so pennylane.ai. We have demos on all of these topics so that you can learn how to do, for example, pulse programming, etc. So definitely recommend it. So QSBT is maybe too advanced for if you are beginning in the space, but if you're already intermediate or advanced, I definitely recommend it. It's a very popular algorithm now. All right, now let's go to a proper quantum machine learning demo. And so then let us just make sure we are all on Pennylane G. And let me mention some other tools and applications. So we have optimization, very useful for variational circuits. There are many applications that can be used on optimization. Of course, there needs to be a clear advantage. Like a lot of people are claiming that quantum computing can do everything. Be skeptical, please be skeptical. There are some cases where there could be an advantage, but you really have to see the cost benefit of using a quantum computer. It's gonna be expensive, and most of the time people are using simulations on classical computers, which is totally valid. But this is not enough to claim quantum advantage. To claim quantum advantage, we need to use an actual quantum computer. And today they're very noisy. So in general, what the field says is unless we fix the noise problem, you're probably not going to see quantum advantage as such. The chemistry side of things is something that we do internally. So we have a lot of tools to help you understand, simulate, etc. Molecules and materials. So battery is one example, but you can use different basis set. You can use given rotations. You can find ground state energies, dissociation energies, etc. We have tutorials for all of this. So if chemistry is your thing, we have a huge section of demos on the website on pennylane.ai that you can go and explore. And if you have specific questions about quantum chemistry, also the forum, you can ask questions there, and we will answer. We answer very quickly. One particular algorithm that has a lot of promise is quantum phase estimation. However, this requires a lot of gates. So you see these huge boxes, it's because they require a lot of gates. So my recommendation would be use something like resource estimation to estimate how many gates, how many qubits you would need to run your particular quantum phase estimation routine, and try to see if there are optimizations that you can do there. So this is something that researchers are doing all the time right now. Like it's an active area of exploration. You can also use the Pennylane data sets for quantum chemistry and spin systems. So you can go to pennylane.ai/datasets, and here's an example of how you could choose this. You can choose a specific number of qubits that you have. You can configure, choose the basis set. So for the chemists, this is very important. You can choose a specific bond length. And then you can download specific data for that specific configuration that you set. So you have run this and created these data sets. And if you know the history of machine learning, you know how important public data sets were for the development of the field. So we hope that these data sets can also be useful and helpful for people doing research on quantum computing and quantum chemistry in particular. In terms of performance, you have access to Lightning Cocos. So you're really lucky to have access to LUMI systems, because it can, except for the wait for today, but it can really make your simulation so much faster. So let me actually, now that we're here, we're still waiting. Okay. So you can you can run circuits, like depending on what GPU you're using, you have some more flexibility. We will need to install other libraries to simulate circuits, but the general recommendation is that if you are going to use GPUs, it becomes being useful if you use more than 20 qubits. So if you have less than 20 qubits, my recommendation would be go with lightning.qubits. If you have more than 20 qubits, then go with try to start using a GPU. That's where you know, you will need that extra power from the GPU, and you will not have, like, the more that you do the back and forth between the CPU and the GPU, the more time it will take. So try to run deep circuits with a lot of qubits. That is when GPUs really shine. If you're interested in compilation, please let me know. We are actively working on Catalyst. It's our newest library. So it's for hybrid compilation of quantum circuits. So it's because we have people that understand the quantum side and the classical side of things, then we're creating this compiler that can help for optimizing the compilation of quantum circuits in particular, that is specifically for this. And we have other tools like circuit cutting. So circuit cutting is something where you can just add like this one line to your circuit, and it can do the equivalent of like cutting it, like breaking it into parts. So it can allow you, if you run out of memory, it can allow you to run larger circuits, or if you have a specific hardware, let's say you have LUMI, which only has 5 qubits. By using circuit cutting, you could run a 10-qubit circuit on a 5-qubit device. So what it does, it basically runs these like parts of a circuit many times. It runs it many times, and then it kind of can do like a putting together of the different parts. So it has an overhead. It has an overhead, but it can allow you to run, larger circuits on smaller systems, or to avoid sometimes the memory problems that you can encounter. And so this allowed us, for example, to run simulations with 100 qubits, it's a big deal. 100 qubits is a lot. So running simulations with over 50 qubits, it's really impressive. And this is because the particular graph that represented this problem presented itself very well to being cut at specific points. So you can see here where it says QAO program graph, you can see that it had kind of like 3 clusters. So if you cut it into 3 different parts, each of these are much smaller than, the full scale problem. So these are the kind of problems where circuit cutting can give you an advantage, especially if you're running out of memory. Now, before we go with next steps, all right.
Yeah.
So hopefully, everything should be installed there. We're going to, so something that we can do is change the number of threads. I know we have 15 minutes, so I'm gonna go first to what really needs to be done here. So something that you can do, because you have access to an HPC system, is you can optimize the number of threads, which is something that if you're used to HPC, you will want to do anyways, but not necessarily having more threads is better, right? So let me first, let's say, I'm going to do vim, and we're going to do x01.pi.
I think you need to load the module first. Use the commands you used before on the script.
I'm sorry?
Module you load Pennylane-LUMI. You need to load the module first.
I'm not on Pennylane-LUMI.
Yeah.
Okay.
You can find them on the chart.
Okay. Module use, yeah. Okay, perfect. Now I should be able to use Vim, right?
Yeah.
All right, so we're going to import Pennylane as QML from Pennylane, import NumPy as NP. We're going to use now the Lightning GPU Cocos device. So dev equals QML.device, and we're going to use lightning.cocos. So we're going to see that it should work. Close this text and wires. Let's start. This is a number of qubits. We're going to try to run a big example. So let's try 20 qubits. Now we're going to do at qml.qnode dev, and we're going to define our circuits. And this case, it can take some weights. So this can actually be an array of several things. Right. Oh, something else. If we want to, because we want to time things at the beginning. So import from timeits, import default. From timeits, import default timer as timer. So we're going to time our example. So we're gonna figure out how much time we can save, or how much more time it will take for, like, with changing the number of threads. Because we're going to use timing, we're gonna run the specific example several times. All right. We're also going to use a different measurement. Maybe I'll show you then when we do the return value. We're going to use a Hamiltonian. So we're going to start in this moment. Like, normally, if you wanted to try also different differentiation methods, you would also add them at the moment of creating the Q node. So after dev, that's where you would add the arguments for using different differentiation methods, for example. Let me move this a little bit. All right. Does everybody see the full screen? Does everybody see everything? Oh. Can you hear me?
Yes, we can hear you.
Okay.
We see the full screen. Yeah.
Okay, perfect. All right, so we're going to start with a template. So we're going to use QML.strongly entangling layers. This creates a lot of entanglement between your qubits. We're going to say weights equals weights, and wires equals range of, well, in this case, 20. We have 20 wires. So in this case, it takes an iterable. So everything we want to learn, it's in the documentation. So if you wanted to learn more about strongly entangled layers, you could land on there. Now we're going to return and the expectation value of a Hamiltonian. So QML.expval, this we already learned. And now we're going to use Hamiltonian. So we can do QML.Hamiltonian. And we can choose, for example, something random. So np.random.rand of, again, our 20 wires. And we would have QML dot polyz. This is again in the computational basis. Remember how before we just measured it for one specific, just for one wire. Now we're going to measure, like do that measurement and return it for all wires. So polyz of I, or I in range of wires. So I know that this is like overflowing a little bit, but hopefully you can see it well. And then we close our parentheses and everything. All right, so we're getting the expectation value. Oh no, I think I'm missing. I might be missing one parentheses. QML dot Hamiltonian. I think I'm missing one parentheses. Yeah, perfect. All right, we're getting the expectation value of a specific Hamiltonian. I could also create this Hamiltonian outside. Probably would be prettier. Great. Now I'm going to define my weights, my initial value for my weights, and I need to know the shape so I can use this nice function. So shape equals KML dot strongly entangling layers dot shape of now in this case I need to decide how many layers I want. So n layers, that's a like, because you have a circuit, you have, you know, a specific your ansatz is going to be like, I have a specific layers that I want to have. So maybe, I know this is very unclear. Let me show you strongly entangling layers here. So I'm going to the documentation of Pennylane. And here I can see, right. Here I can see in templates on the left-hand side, I can go to layer templates and I can see strongly entangling layers. So this is what I'm going to do. I have a number of layers that first have some parameters. So that's why I need to like find the right size for my weights, and the function that I'm using is going to tell me the right size for my weights. And then I have a bunch of entanglement, a bunch of C-knots that will create a lot of entanglement. And yeah, this is just one arbitrary example of something I could use, but I could use also random layers or some other layers if this is something that is interesting for my problem. So anyway, in this particular case, I will have a number of layers. Let's say we're going to have 3 layers, and the number of wires in this case is going to be 20 again. All right, and now my weights are going to be QML, NP dot random dot rand, NumPy random, where the size of this specific random array is going to be the shape that I defined right before. So I've created my Q node. It just has a bunch of entanglement. I've created my expectation value, my return value. So I'm going to measure a Hamiltonian, which is measuring on the polyz axis for a bunch of like for all of the wires. And finally, we get the shape that is going to allow me to get the first iteration, the first value for the weights. So the starting point. Now we're going to do timing starts as empty. And now for let's say t in range of, let's say I'm going to run this 5 times. Let's say I'm going to run this 5 times. So this is just to get an average, to get a proper, you know, a proper timing. I'm going to run this 5 times. I'm going to say start equals, I'm going to start the timer. Now I'm going to choose, for example, I'm going to find the Jacobian. Let's say this is an example of something that I could get. Jac equals QML dot Jacobian of my circuits, and for my weights. And finally, I'm going to end the timer and append this value to the timing. So end equals timer and timing dot append. And now I'm going to do n minus start. Right, so I'm just subtracting the 2 values. And after this, I can just do print mp dots mean. So I'm gonna get the average of timing. I know this might seem a little bit complicated, but I'm just creating a lot of entanglement, measuring and averaging the time it takes, just to show you an example of how to do something interesting on the LUMI systems. Go to explore our resources. Pennylane.ai has everything, but you can go check out the code book. It's great for learning more for the beginners and some like advanced algorithm and so on. So you can find some interesting algorithms there. Our YouTube, if you're more into videos, we have a Xanadu YouTube, which is much more about our hardware. And we have the Pennylane YouTube. It's new, it's super cool. So you're gonna have a lot of fun there. If you're more into challenges, if you're advanced, these can get you like up to speed. Also, the code book has like interactive coding exercises that can help you learn not only the theory, but also the practice of running something on Pennylane. And the demos are like really an amazing resource for the community. So definitely check them out. For those people asking about the residency, you can apply at xanadu.ai/residency. Applications close on December 8th, but please apply early as possible. And if you're more interested in a career, we're always looking for people for great talent and various different kind of expertise. So check it out every so often. We're always having new options available. And there are many ways you can join the community. Slack is a great place to start. You can talk with the community, etc. We also have a Discord. You can join our newsletter. So our newsletter will give you just once a month the summarized information of everything. And our discussion forum, discuss.pennylane.ai. Again, you can find it on the Pennylane website, and it will help you. Like if you have any specific questions, if you're running examples that we did today, this is something that can help you out. And also, please attend QHack. QHack is our main event of the year. It's a worldwide hackathon. It has coding challenges, a hackathon itself. It has streaming sessions. There's a lot of stuff happening, and it's really the one event of the year you shouldn't miss. And it's available online. It will have a small in-person component, but really it's an online event. So make sure to register starting December 5th at qhack.ai. Note it down, put it in your calendar, register for QHack. Here I'm on Visual Studio Code on my computer. So this is one example that I wanted to show you today. So here I created some data between 0 and 2 pi, and some test data, which was a shifted version of that. I created a circuits, a Y gate and a rotation. So this is what I mentioned before. And I would have liked to see you run your circuits to see how you can help your circuit understand the underlying model in the data, right? So your circuit by training could understand that, you know, for a specific output, for a specific input, the output was the sine function. So it could predict properly, you know, the values in my test data. So this was an example. You can find a similar example in a blog post that we have in Pennylane. So really, Pennylane is a place to go where you can find everything. As a conclusion, what I hoped you could see is you should always try to find the right tools for your job. Quantum, classical, CPU, GPU. So today I couldn't show you, but you can indeed use GPUs. If you use over 20 qubits, they're particularly useful, and you can compare the time that it takes with a CPU. And you can also use other tools like changing the number of threads to try to, you know, optimize if you're really at that level, at a very performant level. Quantum is not always better, same as GPUs, and there are some problems that can be good candidates. And here the ball is on your court. Try to bring problems where you have some expertise. So the people who, you know, build quantum are physicists, and they don't necessarily know the same problems that you do. So you're experts probably in a different field, and bringing those problems and exploring it, and being completely transparent of the fact that quantum may or may not be better. That is important. And know that there's no one size fits all. You do need to do some fine tuning, learning about circuits, trying out different ansätze. There are different settings that you will need to work with in order to get a better solution to your problems. And if you do run into trouble, maybe not technical problem like us, but like specific coding trouble, you can always try to find the minimal version that you can, kind of like our Hello World version of the problems that you're having, and then the community can help you better. And there are a lot of tools that you have, you know, available in Pennylane and in the ecosystem to help you with that. So thank you so much.